Welcome to my classes on fundamentals of electrical engineering. We were on the fourth module where we were discussing signals and systems, and we had arrived at the most dynamic and interesting area in signals and systems where we were discussing discrete time domain. And in discrete time domain, we use the Z transform as the most prominent tool for analysis as also for even for computation and understanding. Here, and a very interesting aspect of Z transform happens to be that we set Z as equal to e raised to st. This opens up several vistas. For instance, S can be now equated to what it always was, that is sigma plus or minus j omega. So it has an attenuating component as also a frequency dependent component. That's one aspect. Second is, of course, Z is a complex number. So we have an a plus jb or a plus ib for explaining it. The same e raised to st can now, that is Z is equal to e raised to st, can now be replaced by two components. That's e raised to sigma t multiplied by e raised to plus or minus j omega t. This gives rise to a conversion to a polar system, whereas a plus jb is a rectangular way of describing the same system. So there are several ways or interpretations that you can use, and that's the major benefit of discrete time systems. As I said earlier, the approach is definitely different, but of course it is derived. So let's move on to some of the questions in this session. Again, it's discrete time systems assisted by Z transforms for analysis and solution. So just let us look at the first problem here. Yn denotes the output and Xn denotes the input of a discrete time system given by the difference equation. So just as the differential equations describe the linear time invariant systems in the continuous time domain through constant coefficients, here we have the discrete difference equations describing the discrete time systems again through constant coefficients, okay, for the difference equation. So what is the difference equation? Yn minus 0.8 yn minus 1, so there's a delay there, is equal to the input side xn plus 1.25 xn plus 1. So there's an advancement there. By now, I suppose the advancement as also the delay is clear to you. Its right side impulse response is what? So now we have to solve for it. Okay. Impulse responses, of course, we need to find out Hn. Okay, now we have yz by xz giving us hz, and then that gives you what is called as the impulse response. It may also be called as gz, but if you're calling it hz, it becomes the impulse, the Z transform of impulse response. Okay, so let's see what do we have here. So let's take the Z transform on both sides. So it becomes 1.1 minus, because of 0.8 into Z raised to minus 1. The delay is taken into consideration with the delay unit signified by Z raised to minus 1 yz. That's the left hand side. Right hand side is 1 plus 1.25 Z raised to 1. Okay, so here we are having advance, okay, taken into consideration, and there on the other side we have xz. So yz on one side, xz on the other side. So yz by xz is the hz. Now we call it as hz to get the impulse response. So that's equal to 1 plus 1.25 z divided by 1 minus 0.8 z raised to minus 1. Just an arithmetic operation. So we see, okay, so now to remove the z raised to minus 1, I normally multiply both the numerator as also the denominator by z. Okay, so that we have z plus 1.25 z square divided by z minus 0.8. Okay, so what do we do? So now we can split it into two. We don't need the partial fractions, etc. One component is z by z minus 0.8. The other is 1.25 z square by z minus 0.8. So what does the first component give us? It gives us it gives us a sequence. Okay, that's the speciality of discrete time systems. When you are having z is equal to e raised to st, that t there is the sampling instant, and when you are having a sampler, you are of course going to get the sequences. Okay, so t is capital T. It talks about the uniform sampling rate or sampling period. Okay, so now we have two sequences, one at n equal to 0, the other of course advanced advanced by one time unit, or which occurs at n plus 1. Okay, so now what is asked out of it? It's right side, the impulse response is Okay, is it causal? No, it's not causal. Why? Because we are having an advanced signal. Is it unbounded? We have no. It is not unbounded because all the poles of the pulse transfer function happens to be inside the unit circle. Okay, periodic? No, it's not periodic because it's a limited signal. Okay, it exists. You can see that there is a combination of two signals adding together, and it's a right-sided signal, which itself tells us that it's not going to be periodic. Okay, is it non-negative? Yes, it's going to be non-negative. Why? Because both the sequences, the first sequence is going to be 0.8 raised to n, the other sequence is going to be amplified by 1.25. Okay, and both are, and then of course it's going to be delayed, so it's all going to be more than 0.8. Okay, all the values are going to be larger than 0.8 raised to n. Okay, so that's the first problem, and just one fundamental aspect has been clarified through this particular problem. Okay, so let's move to the second one. A discrete real all-pass system has a pole at z is equal to 2 angle 30 degrees. Okay, this is, as I said earlier, this is the polar representation of a pole wherein it occurs with a magnitude e raised to sigma t equal to 2. Okay, and if e raised to sigma is maintained constant, as in this case, then we have a circle. That's the reason why we have e raised to 0t as a unit circle. Okay, or sigma equal to 0, or a circle without any attenuation. Okay, or a system without or a signal without any attenuation. So z is equal to 2, and it also has an angle equal to 30 degrees. Okay, of course this cannot exist on its own for a stable system or a real system. It should have its conjugate, and the conjugate would be at 2 angle minus 30 degrees. Okay, such that both the real quantities are the same, but the imaginary quantities are both positive and negative. Okay, it therefore also has a pole at 1 by 2 angle 30 degrees. It's not right. Okay, because the pole would be still at 2. Okay, and of course it would have an angle of minus 30 degrees. So let's see. It has a constant phase response over the z planes. No. C. So when we come to C, we see that it is stable only if it is anti-causal. That's right, because a causal system which has a pole outside the unit circle is going to be stable. Okay, this is what it is. But if it is anti-causal, it means that you can simply take the reciprocal of 2. So it's going to be 1 by 2, which is going to tell us that it's a causal system. Okay, so it has to be it is a stable system. So for the system to be stable, it has to be anti-causal. So that's all that's there. Yeah, the diagram tells us that the pole is outside the unit circle in the case of the so if it's a right-sided system, it will not include the unit circle in its region of convergence. On the other hand, if it is anti-causal, it will include the unit circle because it will be towards the insides of or less than 2. Okay, the magnitude will be less than 2, so it would include the unit circle and be stable. So that's the point that we are making clear through this example of gate examination. Let's move to the next question. Which of the following options is true for a linear time invariant discrete time system that obeys the difference equation? Again, the next difference equation, which tells us that yn minus a yn minus 1 is equal to b0 xn minus b1 xn minus 1. Okay, so what does it tell us? Which of the following options is true? Okay, so other than 1, all the options are not true. Okay, yn is unaffected by the values of xn minus k greater than 2. Is it right? No. Why? Because we see that yn is the left hand side is made up of yn minus a yn minus 1. So what is yn minus 1? Every signal on the both on the left and the right will have to be shifted by 1. Okay, so it's definitely going to be affected by signals greater than k for k greater than 2. Okay, so if for xn minus k, okay, that is a perpetual shifting is shown in the difference equation here. I suppose this point is clear. Okay, the system is necessarily causal. No, due to the same argument, you can shift it left side to the left or to the right and the signals, and so you will land up with a non-causal system or an anti-causal system. The system impulse response is non-zero at infinitely many points. That's right, because if you are taking its z transform as is is shown here, yn minus 1. So we see that yz by xn is the same as equal to b0 z minus b1, taking the z transform both sides divided by z minus a. So we see that hn is equal to b0 an un minus b1 an minus 1 un minus 1. So we have many points at which we have non-zero values. Okay, so to have zero values, b0 and b1 should be equal to some extent. Okay, so that is, so we rule out a and b, and let's look at d. When xn is equal to 0, for n less than 0, the function yn greater than 0 is solely determined by the function xn. No, okay, we see that we have the history also being taken into consideration when we describe the difference equation in this particular manner. Okay, so let's go to the fourth question. Point Z has been plotted in the complex plane. So we should have looked at the picture first. What do we have there? Yes, point Z has been marked, and that's a 0. Okay, because a 0 is shown, so it's a 0. It's not a pole. A point Z has been marked in the complex plane as shown in figure below. So the product of the complex number y is equal to 1 by z. Okay, so we have z there, and we want to have y by 1 by z. So how do you describe this? You can describe it as a point inside the unit circle with a positive angle. So it's 1 by z would be a point outside the unit circle, and because the angle that is now being marked by this point z will be on the denominator for y is equal to 1 by z. So the angle will be negative in nature, or it will be in the fourth quadrant. Okay, because this this 0 that has been marked, or the point z that has been marked, is in the first quadrant. So its reciprocal will be in the fourth quadrant. Moreover, it will have a value larger than 1. Okay, because it is 1 by z. Okay, so we have from the four options A, B, C, D. We see that D is true. Okay. So let's move to the fifth problem. Consider a system with following input-output relations. So most of the problems here have been from the via the model of the constant coefficient difference equations, or wherein we are explaining yn in terms of certain features of xn. Okay, so we have here yn is equal to 1 plus minus 1 raised to n xn, where xn is the input and yn is the output, as always. Okay, the system is invertible and time invariant, but it is not invertible. We see that when we are having we need to get back xn from yn. Okay, so but what happens is that some of the messages are lost when we are having minus 1 raised to n, because some of the quantities happen to be negative in nature, and when they add to 1, we lose those values. So you cannot invert, you cannot get back xn from the signals that you have got, which you call as yn. Okay, so I suppose this is clear. What we mean by invertibility is that you get a sequence. Okay, from those sequence you have to go back. Okay, and you have to extract xn of where it started from, or the input, which is not possible in this case. And so we have A, B, C options removed, and we see that D option is non-invertible, which is right. Okay, and it is time varying. It is time varying because we are having 1 plus minus 1 raised to n. Okay, so I suppose minus 1 raised to n xn. Okay, so xn is the occurrence of xn varies according to the value of n. Okay, so that's the reason why it is time varying. Okay, so let's move to the sixth problem. What do we have here? The pole zero plots of 3 discrete time systems P, Q, R on the Z plane are as shown. Okay, so we have 2 poles. Yeah, okay, so we have in PQR we have 2 poles. Okay, yeah, 2 poles are on the origin, and we have 2 zeros. They are on the extremes of the unit circle. Similarly, we have in all cases we see that the zeros are on the extreme cases of the unit circle, but the poles progressively move from on j omega axis. From omega equal to 0 to omega equal to 0.5 to omega equal to 1. Okay, so this is the situation, and so their impulse responses have been explained as HPZ, HQZ, and HRZ just from the pole zero diagram that has been given to us. Okay, which one of the following is true about the frequency selectivity of these systems? of these systems. So what do we see about these systems? We see that they have two poles and two zeros in all cases. So they are all band pass filters. Okay, so this is the frequency selectivity that we may have from the four options. What are they? All three are high pass filters? No, because there is a limitation when you are looking at when you're comparing the poles and zeros. All three are band pass filters? True. So we stop there or we go further. All three are low pass filters? No. P is a low pass filter, Q is a band pass. No, all of them are band pass filters. Okay. So I suppose the logic is clear. We have two poles and two zeros, okay, complementing each other. So we have what is called as a band pass filter. The seventh problem, the Z transform of a sequence Xn is given as Xn is equal to, now we have a sequence here, not a model for the system explained by a difference equation. Here we have just a simple sequence alone or a signal alone. Okay, Xn is given as Xn is equal to 2Z plus 4 minus 4 by Z plus 3Z cube. So the 3Z square. What do we notice here? We see that it is a non-causal system. Why? It's a non-causal signal because we have 2Z. Okay, and if you multiply throughout by Z square to get the right-sided portion as well, then we see that we have a really causal anti-causal system. Okay, if Yn is the first difference of Xn, then Yz is given by. So what do you mean by first difference? First difference is given by Yn minus 1. That is the delayed signal removed subtracted from the sequence as it is. Okay, so Yn. So Yn is Yn. So we have Yn minus 1 as described by so in the Z transform domain, it is going to be Yz minus Z inverse Yz. Okay, so you have to multiply by Z inverse to get the corresponding Z transform of Yn minus 1, and then you have to subtract. Okay, so we have two extremes for the function as given in the Z transform domain. We have the one with the largest exponent as also the smallest exponent for Z. Okay, so what do we have here? So we have several options. So rather than computing everything, it's better to go for the two extremes. So what do we have at the two extremes? At the very other end, we see that we are going to have we have 3 Z raised to minus 2 as such. Okay, and when you multiply it by Z raised to minus 1, you are going to get Z raised to minus 3. Okay, so we are going to have minus 3 Z raised to minus 3. Why? Because Yn minus 1 is subtracted from Yn. So the last term in the Z transform of Yn minus 1 should be minus 3 divided by minus 3 Z raised to minus 3, or minus 3 divided by Z cube. Okay, so we see that A and B of the four options, A and B one of them may be right. Okay, the other two can be discarded. So now we move to the other end. So we go to the other end. Why do we go to the other end? Why? Because for A it is going to be 2, and for B it's going to be minus 2. That the coefficients are going to be, the constant coefficients are going to be 2 and minus 2. So we just go to the other end. What do we have there? We see that it is going to be 2Z minus 2Z plus 4 minus 4Z plus 3Z square, 3 by Z square, minus Z inverse multiply Z raised to minus 1 multiplied by the same function. Okay, so we definitely 2Z will have nothing. So we have 2Z as the starting of the sequence. Okay, so that comes in option A. So we go for option A as the solution. I hope it's clear. We go to the two extremes only because it's a gate examination context, and we solve for so we filter out two more possible answers, and then we go to the other end. We observe whether they are different in the from these two answers. If they are different, you go for calculating them. Okay, and the two extremes are good in the sense that one is of course going to be minus 3Z cube. The other extreme is going to be simply 2Z. Okay, so I suppose this is also clear. Now we go to the so now we go to the 8th problem. What do we have here? We have we seem to have two systems connected in cascade, which means that convolution may be useful, or if you can multiply the Z transforms of both. Okay, so what do we have here? A cascade system having the impulse response h1n is equal to 1 minus 1. So we have h1n as equal to 1 minus 1. Okay, so this is the sequence, and h2n as equal to 1 and 1. The arrows show where they start. Okay, so now we can the same sequence that we have got, we can convert to Z transform by seeing that 1 arrives first. So we have 1 there, and then we are having what is called as a delayed sequence of amplitude minus 1, delayed component of h1 with an amplitude equal to minus 1 but delayed. So we have 1 minus Z raised to minus 1. What about h2? H2 can be similarly converted into 1 plus Z raised to 1 plus Z raised to minus 1. So the first signal, the arrow that is shown tells us that this is at n equal to 0. The other is going to be a delayed signal. Okay, so it has already arrived. Okay, so we have what is called as 1 minus Z raised to minus 1. The other is 1 plus Z raised to minus 1. Okay, and so you can multiply them together. Why? Because these two systems are cascaded. So what do we have? This is as simple as 1 plus x into 1 minus x. So we have 1 minus x squared. So in this case, it's going to be 1 minus z squared. Okay, Z raised to minus 2. So 1 minus Z raised to minus 2. Okay, so now what is asked, as shown in the figure below, where symbol shows the arrow shows the time origin, as we guessed. Okay, the input sequence xn for which the cascade system produces an output sequence. Okay, so we have an output sequence as given by 1 2 1 minus 1 minus 2 minus 1. So with this also we can convert into yz by looking at the time sequence. So we have 1. Okay, then next is amplitude 2. So 2 into Z raised to minus 1. Then it's going to be 1 into Z raised to minus 2. Then it's going to be minus 1 Z raised to minus 3. And then minus 2 Z raised to minus 4 minus Z raised to minus 5. I hope this is clear. You start with the first the time origin, and then each delayed signal you multiply by the delay units Z raised to minus 1 for each consequent delay, and so you arrive at yz as well. So now we have yz. You also have what is called as the totality of the two systems cascaded together as hz is equal to, okay, which is h1z multiplied by h2z as equal to 1 minus z square. Okay, so and we require what is called as the what we call as what started it all off, or the input xn. Okay, so how do you do that? Okay, just by comparing the sequences you can do that. So what do we have here? So first, of course, the signal moves in, that is 1 minus z raised to minus 2 moves in, and so we see that we can have what is called as the last of the since it is minus z raised to minus 2, the last would the biggest component in xn is going to be the most delayed quantity is also going to be minus. Okay, so we see that we can have 1 there. Okay, similarly, the first quantity is going to be 1, the constant is going to be 1. In this case also it's 1, so the first quantity is going to be 1. Okay, so we go for A and D. Why? Because we see that the first and the last of the sequences, that is the first that n equal to 0 and n equal to 4. Why 4? Why? Because we see that we have 5 components as the 1 2 3 4 5 6 components as the output, and we have only 2 here, so we need to have 4 there such that together they can give rise to so many. Okay, so we see. Okay, so of course first we remove option C because it has only 3 components. Okay, so then we go for then we go for A and D. Why? Because B has 2 at its as the signal which is delayed by 3 time units. Okay, by 3 time units. So from now we have to go for what is called as the signals that are in between. For that it's much easier to compare the last but 2 components, both in the both at n equal to 0 as also at n equal to 5. Okay, so we see that we have so we have 2 and minus 2, and we see that 1 that is h1z hz needs to be multiplied by 2 for the constant, and for the negative component it has to be again multiplied by 2 to get these responses. So the two internal signals will be 2 and 2. So 1, 2, 2, 1 will be the components of x as can be obtained by just comparing the impulse response which works on it and the output response which comes out as a result of the impulse response working on the input signal. Okay, I hope this is clear. It's better that you do it again just by looking at this slide and comparing this kind of observations and get to the problem easily rather than dividing and obtaining the solution. Okay, so of course you can divide and also obtain the solution. Okay, so what do we have here? An input signal xt is equal to 2 plus 5 sine 100 pi t. So there's a DC component. There's also a sinusoid component. Okay, is sampled with a sampling frequency of 400 hertz. Okay, 400 hertz means what in comparison with the sinusoid component? What about the DC component? It is going to be sampled at 400 hertz, means that you are going to get a value of 2 at all times. Okay, what about the sine component? Sine component, it is the omega part is 100 pi. Okay, or that is equal to 2 pi f, or 50 hertz happens to be the frequency of the sinusoid component. Okay, and it's going to be sampled at 50 into 8. Okay, 50 into 8 times the frequency, because 400 hertz happens to be the sampling frequency. Okay, and applied to the system whose transfer function is represented by yz by xz is equal to 1 by n. Okay, 1 minus z raised to minus n divided by 1 minus z raised to minus 1, where n represents the number of samples per cycle. Okay, so when you are sampling such a sinusoid by or even the DC component, of course, is going to be sampled all through because 2 is remaining constant. But this is a sinusoid, so the sinusoid is going to be sampled 8 times. Why? Because the frequency is 50 hertz for the sinusoid, but for the sampling frequency is 400 hertz. Okay, so it's going to be sampled 8 times. So we have n as equal to 8. Okay, so 2 is sampled at 2.5 milliseconds because 400 hertz corresponds to 2.5 milliseconds. Okay, for the sinusoid with 8 samples per period, the sampling period is going to be given by 2 pi by 8 or pi by 4. Okay, so far so good. Now we go for what is called as HZ. Okay, so we require the output by the system under steady state. So let's look at HZ, which is going to work on the input and convert it into the output. Okay, so HZ is the same as equal to, as is given, 1 by yz, as is given by yz by xz is equal to 1 by n. So 1 by 8, 1 minus z raised to, so e raised to minus j. Okay, because we realize that it's a sinusoid that we are doing, so we need to replace z by e raised to minus z by e raised to st, where z now sigma is removed, and so only omega comes in. So we have minus from z raised to minus n, and then we have j omega naught as was given by as was computed, and then we have 8 as well because n is there. Okay, on the denominator we have 1 minus e raised to minus j omega naught only. And what is omega naught? Omega naught is equal to pi by 4. So pi by 4 multiplied by 8 gives you 2 pi. Okay, so e raised to minus j 2 pi is going to be equal to 1. So 1 minus 1 is going to be equal to 0. Okay, so the numerator has 0. So we don't compute anything because HL is equal to 0. Or in other words, only the DC component is sampled and this continues to be sampled. And so from amongst the answers, we see that output of the system will be corresponding to a sequence equal to 2, and this value of 2 will continue to go out. Okay, so this is what we have done today. This is the very interesting nature of doing problems in discrete time domain, because each of them give you a different kind of perspective, and you need not do the computations at all. Of course, if you understand the details, and I have tried to give you the details, especially in this particular problem, wherein we see that the filter that we have placed here with the z transform or hz as given by 1 by n into 1 minus z raised to minus n divided by 1 minus z raised to minus n is now facing a signal which is now being sampled 8 times, or in other words, the omega naught that is happening for the sampler happens to be pi by 4. Okay, so if it is pi by 4, we see that 1 minus z raised to minus n, okay, that is the numerator, becomes equal to 0, or the the entire effect is going to be that it's a no pass condition for the sinusoid. But for the DC component, which has no such restrictions, we see that it is going to be passed altered. Okay, we also looked at problems like cascaded systems, and we just compared sequences in two problems. Okay, the extremes essentially, and from the extremes we tried to glean out what is going to be the signal which is not in evidence. Like for instance, the input was not in evidence for one case. For the other case, we tried to find out what is going to be the output when you are having a first difference coming there. Okay, we also had a look at the location of the poles for different systems, and some one aspect of invertibility was also examined. Okay, so I suppose by now the very dynamic as also very vast as at the same time deep kind of understanding for discrete time systems are going to help you a lot, is what I would like to convey through this session. And there is another session in the same genre, and I hope that you will gain a lot. Thank you.